So we got a sense now of how we're doing numbers in this world. We talked about scientific notation, a way of representing numbers where we can look at it and understand it a bit more because we break it into a number between 1 and 10 as the coefficient, and then some sort of exponent which tells us, is it a really big number, is it a really small number? Big numbers have positive exponents, small numbers have negative exponents. What we're going to talk about next is, what about all the rest of those numbers in there? When I converted this guy to scientific notation, going back to our galaxy, I only kept the 9, the 4, and the 6. I didn't keep any of these other zeros as part of my coefficient. And why not? What's special about those zeros that I did not include them? And what's special about the 9, the 4, and the 6 that I did include them? So let's look at this lovely picture of our galaxy up here. Now, what I'm going to do is I'm going to start at one end of the galaxy over here, and I'm just going to walk across the galaxy to this end over here, right? And what that says is I just walked 9.46 times 10 to the 19th meters. If I did that, it might take me a little while to do, but I did it. Now, here I am on the edge of the galaxy, way over here, you can see. In fact, I have to go a little bit further because there's a little bit of dust out there. Now, I'm going to take this last piece of dust, right? I went 946,000,019, 10 to the 19th. And there's a piece of dust over here that marks the end of the galaxy. I'm going to take that dust and I'm going to move it over here. And I moved it 1 meter away. So here's the question. When I write, right, so I made the galaxy longer. That's pretty cool. I just walked to the end of the galaxy. I made it longer. When I write that, am I now going to write this with 946,000, and am I going to put a 1 here because I just made the galaxy 1 meter longer? So stop to think about that for a sec. Should I put a 1 there because I made the galaxy 1 meter longer? Most of you probably thought about it and said, well, maybe, but it's the galaxy. I mean, 1, is that really going to do anything? And maybe not. Okay, so I'm not going to move it a meter away. I'm going to move it 100 meters away. So I'm going to move it this one right here. So 100 meters. That's more of a distance there. Should I put a 1 there now to say that I moved it 100 meters? And again, people are like, yeah, well, does it really make that much of a difference? Maybe I would, maybe I wouldn't. Okay, so let's be bold here. 1 0 0 0 0 0 0 0. How many zeros do I have? I have 1 2 3 4 5 6 7 8. 1 2 3 4 5 6 7 8. I mean, that's a long distance. That's like astronomical sized distances, right, inside our solar system. Should I put a 1 here? I took that last thing, I made the galaxy that much larger. It's a big number. If you had that many dollars, you'd be set for life, right? Do I need to change that number to a 1? And again, the answer is probably not, but you're not entirely sure why at this point. This point is getting a little more fuzzy as to why not. When it was 1, most people are like, yeah, no, you don't have to do that. But up here, you're like, well, that's a big number. Didn't I change it by a lot? And the answer is that no, I don't have to change it. I wouldn't have to change it if I made it that much longer. I wouldn't have to change it if I made it that much longer. What is it about those zeros? Well, it turns out those zeros right here, no one measured them. And you're like, well, yes, they did. Right? They had to measure these zeros, otherwise they wouldn't know how long the galaxy is, and they wouldn't know it's 9.46 times 10 to the 19th meters long. So those zeros were measured. And what I mean by measured is that somebody actually knows that the value of that 0 is 0. This number right here, that one, it could be a 9, and no one knows. No one knows. We have no idea if that number is a 9 or 3 or 2. But we have to put that 0 there. Why do we have to put that 0 there? Because if we didn't put any zeros there, if we said, hey, if we don't know what it is, don't put it, then the galaxy would be 946 meters long, and we could walk across it fairly briskly and back and forth. And imagine if you just had to walk across the galaxy every day, back and forth, back and forth. It'd be like being in quarantine. Okay, so we have to put those zeros there. Right? We have to have 946,000,000,000,000. What are those zeros telling us? They're telling us that we have a big 946. They're telling us that this 946 we have is huge, because if I didn't put those zeros there, I'd say, well, I've just got 946. But with those zeros, it's a huge number of 946s. But it turns out the 9, the 4, and the 6, people actually measured those. They know that that number's a 9, they know it's a 4, and they're pretty sure it's a 6 as the next number. So how do we distinguish between these measured numbers, the ones that look kind of significant, and these other ones which are zeros, which are important, right? Because if I didn't have them there, the galaxy would only be 946 meters long. How do I distinguish between those two? How do I distinguish between these significant ones and these ones that are important but maybe kind of insignificant, right? What's the difference between important and insignificant? And turns out that's what we call these things. We call them significant figures. Those numbers that we actually measured, and we know it's a 9, we know it's a 4, we know it's a 6, those are what we call significant figures. All those other zeros, we call them insignificant. Now, you have to be aware that that's not the same as saying unimportant. It's not that they're not important. They're very important. The galaxy is that many things with a bunch of zeros at the end long. We just don't know any of those zeros, whether they're zeros or 9s or 3s or 4s. And so what we have to do in that case is just put a 0 there so that we get the big number that we want and say, hey, the 9, the 4, and the 6, we know something about those. The zeros just tell us how big it is. So we have significant figures and we have insignificant figures. And most of the figures in the galaxy are insignificant. Important, but insignificant. So how do we represent what's significant? And just like many other things, there's rules for doing this. Rule number 1 is that all non-zero numbers are significant. All non-zero numbers are significant. So whenever I write a number and it's got a 3 or a 7 or a 4, I'm telling someone I measured that number, or someone I know did. I measured that number and it is a 3 because I measured it, I took a ruler out, I know that's a 3 or a 7 or a 4. Okay, so all non-zero numbers are significant. One of the things that we end up doing quite a lot, and you'll see why in a little while, is we don't necessarily need to know whether this digit's significant or that digit's significant. We just need to know the total number of significant digits in a number. So if I write a number 4,325, I might want to count how many significant figures are in here. And if all non-zero numbers are significant, I get that this number has 4 significant figures. And wow, it took a long time to write down the word significant figures, and the picture of my head just cut it off anyway. So that's a really long thing to have to write. Scientists, we like to shorten things. We like to make things quick, easy, fast. And so you'll see people write, instead of significant figures, they'll just write sig figs. But even that's, a whole 7 characters. And so even better is to write SF. Say, hey, this number has 4 SF. Very quick, very easy to write. And 4,325 has 4 SF. How about 36,974? How many significant figures does that have? Well, all of those are significant, and there's 5 digits, and so this number has 5 significant figures. So there's all non-zero numbers. So our rest of our rules got to be dealing with zeros, and that's what happens. The next rule, number 2, is that zeros between non-zero numbers are significant. Right? Sometimes we measure something and it's 0. Right? And we need a way of telling somebody that 0 is actually measured as opposed to just there for scale. So if I have a number like 405, this 0 in the middle between 2 non-zero numbers is considered significant. And what I'm telling someone is, I know it's a 4, I know it's a 0, and I know it's a 5. So this guy has 3 significant figures. It also works for decimals. So if I have 0.40085, these zeros, even though there's 2 of them, are sandwiched between non-zero numbers. And some people do call this the sandwich rule. They're sandwiched between non-zero numbers, so all those numbers are significant, and this guy's got 5 significant figures. And again, those zeros, somebody measured those, and that number should actually be 0 because we measured it to be 0, as opposed to just being there to tell me how big or small the number was. So there are more rules with regards to zeros because there's two cases we haven't considered. What about leading zeros? Leading zeros are never significant. And again, significant and important, two different things. They are never significant, but yes, they are important. So if I write 0.00419, what are these zeros over here? These are the leading zeros. They come before the first significant figure, before the first non-zero digit, which is my 4 there. So these guys, although important, because if I didn't have those two zeros there, I'd have a different number, they are not significant, and we're only going to count these guys and say, hey, I've got 3 significant figures. We can combine that with other rules. And get 0.000048009. All these leading zeros are insignificant. Important, you've got to write them there. They're part of the number. But when I'm counting significant figures, I don't count them. No one measured this guy to be 0. They measured the 4, and I need a really small 4. How you get a really small 4 is by putting a bunch of zeros before it. But all of these ones are significant. We've got non-zero digits. We've got sandwiched zeros. And so we have here a total of 5 significant figures. So leading zeros, never significant. And our last one are trailing zeros. And the trailing zero rule is the hardest rule because it has 2 parts to it. Trailing zeros are not significant. You're like, that doesn't sound too bad. Unless there is a decimal point. Then they are significant. So trailing zeros are not significant unless there is a decimal point, then they are significant. You're like, whoa, that's a little weird. I call it the magic decimal. So let's do a couple examples because examples are usually the best way of clarifying rules. 18,000. When we write the number 18,000, we know that the 1 and the 8 are significant because they are non-zero numbers. What about the zeros? Well, the zeros here are trailing zeros, so they are not significant. Important, absolutely important. If I don't write the number, I have 8. If I don't write the zeros, I have the number 18. With the zeros, I have the number 18,000. Very different numbers. So important zeros, but not significant zeros. Nobody measured that third 0 and knows that it's 0. It could be a 4, it could be a 7, it could be a 3. We don't know, we don't really care. We just know that we have 18,000, and that's got 2 significant figures. All right, if you've got $18,000, do you really care if you've got $18,001? Probably not so much. Okay? That last digit might not be all that significant to you. All right, so 18,000, 2 significant figures. How about 346,700,000? 346,700,000. Well, we know all of these guys are significant. And then these guys, since there's no decimal point, they are not significant. And so this number has 4 significant figures. We can combine this with other rules. 0.003050. Ooh, lots of rules in one. Leading zeros, never significant. We know these guys are significant. We know this sandwiched one is significant. But now what we have is we have a trailing 0 here because it's after the last non-zero number. That's how we know it's trailing. It's after the last non-zero number, so is it significant? Well, if you look back here, there's a decimal point present. And because of that decimal point, that trailing 0 is significant, and we have 4 significant figures. We're telling someone by writing that 0 at the end that we measured that 0. And it's a very different thing from writing this guy, which only has 3 significant figures. What we're saying when we write 0.00305 without the 0 at the end is, I don't know what that next digit is, and I don't really care. Okay? But when we write that 0 at the end, we're saying, I know that digit, and I know it's a 0. So mathematically, you type either one of those numbers into your calculator, and it's the same to your calculator. But to a scientist, they're two different things, because in one of them, I know something about that last digit, and in the next one, I don't know anything about that last digit. One other thing that does crop up occasionally, but not too often, what about if you have the number 250? Well, I think by now you've got, hey, that's 2 sig figs, trailing zeros, not significant. But some people will sometimes write that, 250 dot. And the mere presence of the decimal makes that trailing zero significant. And you have that number has 3 significant figures. So 250 has 2 significant figures, but 250 dot has 3 significant figures. So the decimal point can be pretty important, pretty magical. When it's there, it makes those trailing zeros significant. When it's not, they are not significant. In numbers less than 1, then you always end up with a decimal point, because there's no other way to write a number less than 1 as a decimal without a decimal point. You always end up with trailing zero significant. For numbers greater than 1, you only end up with the trailing zero significant if there is a decimal point. Here's some examples. Encourage you to pause, write these down, write down how many significant figures are in each of those numbers, and then check your work. All non-zero numbers, we got 4 significant figures. Sandwiched between 2 non-significant numbers, trailing, but there's a decimal point. That makes the trailing one significant, so everybody's significant. It's like Oprah, 1, 2, 3, 4, 5, 6. Everybody gets a new car. There we go, 6 significant figures. How about the next one, 0.00350? Leading zeros, never significant, whether or not there's a decimal. Trailing zero is significant because there's a decimal, and this one has 3 significant figures. Ooh, scientific notation, we haven't talked about that one yet. When counting significant figures for scientific notation, you're going to ignore the exponent. Doesn't really matter what the exponent is. The coefficient is what tells you how many significant figures you have. So if we look at 6.530, it's got a decimal point, which makes that trailing zero significant. And so this guy has 4 significant figures. So for scientific notation, you always get significant figures off the coefficient. 150, trailing zero, no decimal point. So it is not significant, and we just have those 2 significant figures. 870,000, those guys are not significant because there was no decimal point. So those are only 2 significant figures that we get for this problem. Hello, computer. There we go. Your turn. How many significant figures are in 0.03050? Try it out. Really? Okay. Leading zeros, never significant. Trailing zero, significant because there's a decimal point. So you get the 3, the 0, the 5, and the 0 are 4 significant figures in our problem. We also have a need to round numbers a lot in this class. So we'll talk about some rounding rules and why we're going to use them in our next section. So for rounding, what we use in science, mostly in the world, is basic rounding. That if the next digit that you're trying to round is 4 or less, then you round down. You keep your digit the same. If the next digit that you're trying to round is 5 or greater, 5 to 9, then you round up and you make your digit 1 bigger. So I'm going to blow this up. If we took 3.823, rounded it to 1 decimal, what we're going to do is I'm going to draw a box around the number I'm going to keep. And then I'm going to look at this next number, which is a 2. And the number 2 says I'm going to round down, which means I'm going to keep the number that I had, and I just get 3.8. But if it's 5 or greater, then I need to change what I do, and I need to round it up. So I've got 3.8 here, but my next digit is a 7, which means I need to round my 8 up to a 9. Why did I draw that box? Because it said 1 decimal, and so I drew a box covering all numbers to where I was ending up. Rounding 3.592 to 1 decimal is like that. I look at my next number is a 9, which means I'm going to round my 3.5 up to 3.6. Rounding 3.592 to 2 decimals. Draw a box around what I want to keep, the 2 decimals. I look at my next number. It says it's less than 5, which means I'm going to keep my number as is and just get 3.59. Now, more often what we're going to find is not, hey, I want to round this to 1 decimal, 2 decimals, but I actually want to round things to a certain number of significant figures or significant digits. I'm going to do it the same way I was just doing it. I'm going to draw a box around what I want to keep, look at the next number, and decide what I do to my box. So it says 3 significant digits, so I drew a box around my first 3 significant digits. I look at my next number, it's 5 or greater, which means I have to round up this guy, and I get 28.3. So that's how we do rounding. We're going to see this a lot. Rounding to the correct number of significant figures is an important thing when we're dealing with numbers, especially measured numbers from the lab. Your turn. What's 18,485 rounded to 3 significant figures? All right. Hopefully you got a chance to try it. 18,485, let me write this down. 18,485. If you just did what I told you in the last one, you'd be like, hey, I'm going to box that. I'm going to look at my next digit. I'm going to round this guy up, and I get 185. And you might have answered B, and that would be incorrect. And here's why. If you had $18,000 in the bank, and the bank said, you know, we're having some computer issues. It was rounding our bank accounts, but it should be okay. And you got rounded down to $185. Would you be a little upset? You would. You'd be absolutely upset. I had $18,000. Now I've got $185. No. But if you were rounded from 18,485, what would you think we would be rounded to? How about 18,500? You need those important zeros afterwards. They may not be significant, but they are important. And so when we've got these large numbers and we're rounding them, so right, I round 185, I also need to bring down my zeros to make sure that the number I round to is very close to the number I started with. So I started with a number in the 18,000s. I should end with a number in the 18,000s or so. So I end up with 18,500, not 185. And I apologize for tricking you, but sometimes that's the best way to do things. Okay, how about this one? What is 0.8190 rounded to 2 significant figures? So again, a little bit different because we haven't done scientific notation in rounding yet, but it works the same way. Okay. 0.8190 times 10 to the minus third. I'm going to go ahead and round first and then convert to a decimal, because you notice all of our answers are in decimal. But you could just as easily convert to decimal and then round. You'll get the same answer. I want 2 significant figures. That leading 0, never significant, so I'm going to keep these 2 guys here. I'm still going to copy down my leading 0. I'm going to copy down my decimal. I've got an 8, and then I round up because my next digit is a 9. So you might be tempted at this point to be like, hey, 0.82, and you'd be wrong because we still have this times 10 to the minus 3 over here. What does the 10 to minus 3 tell us to do? It tells us to move this guy over 1, 2, 3, fill in a couple of zeros. There's my decimal point, and I get 0.00082, which is C. So a whole lot of rules. Right? How do we count significant figures? When are they significant? How do we round them? We're rounding them to the right number of digits. Are we rounding and we pulling these zeros down? There's so much to think about. Why do we care? Why do we care about rounding numbers and doing all these things, knowing whether they're significant or not significant? And it turns out it has a lot of importance in how we handle the numbers and how we think about the reliability of our answers as we calculate problems. So an example I give is just this. Let's say you wanted to know the weight of an M&M. The weight of an M&M, you go and you buy yourself a cheap kitchen scale. Most of those read to about 0.1 grams, and you find that the M&M weighs 0.8 grams. But if you want to know a little bit better than that, you can go out and buy yourself an analog balance. Now, I also found there's some pretty inexpensive digital balances out there. But an analog balance that gets you that extra digit of 0.85 grams is going to run you a few $100, so it's a little more expensive. Now, let's say you really wanted to know the mass of that M&M really well. You went and get yourself an analytical balance for several $1,000s. You can get 5 digits after the decimal. Wow! So there's something to be said that the more precisely you want to know something, the more digits that you want to know, like, hey, I measured this, I measured this, I measured this, the more you have to pay for it, or the more work you have to do. So there's something to be said for, there's a difference between saying 0.8 grams and 0.85135 grams. In fact, even if the answer over here were 0.80000 grams, mathematically exactly the same as what the kitchen scale gave you, this number has all those extra measured digits. We know that's a 0, we know that's a 0, we know that's a 0, and so it's giving us more information. So if we do math with these numbers, there's going to be a difference between the numbers we can talk about in our answer when we only knew one digit to begin with. We only knew it was 0.8. We didn't know the third or fourth digit. And when we do know the third, fourth, fifth digit, our answer has to reflect what we know about things. An analogy that you can use is that if you're baking something and you put one measurement very precisely, one measurement kind of bleh, how well are you going to be able to know what you had in total, right? You're only going to be limited by the measurement that you did poorly on. And we'll see that going forward when we actually do the math of how to do significant figures when we do addition, subtraction, multiplication, division, and all those things. So our summary of this is we learned what significant figures were. We learned that they are numbers that we actually measured. We talked about insignificant digits, which are sometimes very important, right? 18,000, you better put those zeros at the end there, because otherwise you've got 18, but they are not significant. No one knows if that third 0 is a 0 or a 7 or a 5. We don't know. And then we talked a little bit about why we care about those significant figures and also how to round numbers. In the next section, we're going to talk about doing math with these numbers. How does it change how we do the math here? Thanks so much.